In this lesson, we will look at how even the smallest dimensional deviations of a component can have a negative impact on the quality of a product. And hello again to this lesson, which essentially has 3 learning objectives. In the end, you should have understood why it makes sense to keep deviations from an ideal as small as possible, and that any deviation from this ideal can mean a loss of customer satisfaction. Furthermore, you should know that processes have a process center or process mean and are subject to variance. You will learn the relevant definitions and understand in general terms how changes in these parameters can have a negative impact on the product. You will also get to know a procedure which is used to make a quality statement about a process. This lesson is divided into 3 chapters. In the first chapter, we look at an example that very clearly shows the connection between a dimensional deviation and the satisfaction of a customer with the final product. With this, I want to emphasize that anyone who has an influence on the production of a characteristic also has a significant influence on the quality of the overall product. In the second chapter, we continue with the example to explain the concepts of precision and accuracy. In the last chapter, we go through, albeit only very superficially, the steps that are required to make a quality statement about a process. Let's start with the example where we use oil consumption of a car to look at how the quality of a single component affects a customer's satisfaction with the finished product. Please imagine you are driving a certain distance in your car, for example, 1000 kilometers. After 1000 kilometers, a warning light comes on, telling you that the oil level is too low. So you drive to the nearest gas station and fill up a liter of motor oil worth 20 euros. Then you continue your journey, and after you have driven another 1000 kilometers, at some point, the same thing happens again. The low oil warning light comes on again. So you drive to the next gas station and again refill 1 liter of engine oil worth 20 euros. And so it goes on and on, unfortunately with a nice regularity. You always have to top up the engine oil after about 1000 kilometers, so that after a year you have topped up engine oil worth 1000 euros. You take this as an opportunity to take a closer look at the specification of the vehicle. And there it says on some page that the oil consumption can actually be up to 1 liter per 1000 kilometers. So everything okay? Well, hardly, or? Because we as consumers have a very clear idea of what we expect from a product and what we mean by quality. In this case, my expectation is that my car will not use any oil at all, no matter what any specification says. So, if I have to pay for extra oil, I'm not happy. And with that, we have already made the following very simple connection. The more a product deviates from one's expectations, the more dissatisfied one is with the product. Yes, you now could say, you could have known that beforehand, and so on and so forth. But that doesn't matter for the basic context. If you now carry out a cause analysis as to why the engine consumes so much oil, then in this very simplified example, you come to the gap between the piston and the cylinder wall, through which oil can ultimately escape into the environment. And the smaller the diameter of the piston, the larger the gap. So here we have a very nice, because descriptive example, how a single dimension of a component has a significant impact on the customer's perception of the quality of the overall product. And that's ultimately what it's all about, keeping such deviations as small as possible. When we talk about deviations, we also have to talk about which changes can lead to such deviations. And that's what this chapter is about. Let's go back to the example of the engine and its oil consumption. Very, very simply, in the system under consideration, we have an oil supply, the engine block with its cylinder wall, the engine piston, and all around the environment. As previously stated, while the engine is operating and the piston is moving up and down, oil can leak into the environment through the gap. The oil consumption is determined by the gap size. The size of the gap, in turn, essentially depends on the diameters of the piston and the cylinder. So, if the diameters have a significant impact on the quality of the motor, more generally it can be said that the quality of any product depends on the variability of the characteristics of its individual parts. Ergo, this variability should be kept as small as possible. Let's assume that there is an ideal size. In the case of the piston, this would be perhaps a diameter of 60.0000 period millimeter. No process in this world could ever reproducibly produce such a dimension. Due to various influences, there will always be deviations in one direction or the other. And for this very reason, we now need to talk about the terms accurate and precise. The circles shown here with the blue dot in the middle should be a target. The black crosses are the marks of a shooter. If all hits are exactly in the middle, one can say that the result is both precise and accurate. But what exactly is the difference? The result of another shooter with the same rifle is shown here. Probably the shooter trembled a little from cold or excitement. His hits were evenly distributed around the center, but deviate more from it. That means the spread is greater. So it was hit less precisely. Ideally, however, the blue center of the target should always be hit. Precision describes the degree to which the values differ from each other, so how much they spread. Let's go back to the score of the first shooter, who landed all the hits in the middle. Now this shooter switches rifles and lands all hits off-center. That means it's not accurate. Accuracy describes how close the center of hits is to the center of the target. This result is not accurate, but it is precise. Again, precision is the degree to which hits differ from each other in the repeated shots. Probably only the rifle scope would have to be realigned, and the shooter would always hit the center precisely and accurately. Of course, the various influences can also overlap and lead to results that are neither accurate nor precise. For example, a trembling shooter with a poorly adjusted rifle scope. In the practice of a manufacturing process, this means that both the process center or process location and the spread of the process results are monitored. Without going into more detail about the distribution of values and their interpretation, the following should be clarified here. The blue curve shows the distribution of measured values for different parts. Ideally, the spread is small, that means precise. The middle image shows a broader curve and thus a greater spread. A process with such results is therefore less precise. In the picture on the far right, the process location is slightly shifted. This process is therefore a little less accurate compared to a process in which the process location is exactly on the target value. You will find more about the distribution of values and the evaluation of processes in the other lessons. If we apply what we have just learned to the case study from the beginning, and it is our goal that the customer is as satisfied as possible with an end product, then it is necessary to keep deviations as small as possible. In other words, to keep deviations in the process location and process spread from the ideal as small as possible. After looking at how important individual product characteristics can be, in this chapter we want to take a very rough look at the individual steps that you would go through when you want to make a statement about the quality of a process. The diameter of this piston should again serve as an example of a product characteristic. Such a characteristic is known as a variable characteristic. This means that the diameter can have any intermediate value. The target dimension should be 60.1 mm. This nominal dimension may deviate by 0.1 mm to the upper side or by up to 0.1 mm to the downside. The piston is to be made from a semi-finished product by turning. Like all processes, this process is also subject to disturbances, as a result of which the diameters of the various pistons differ from one another. Such disturbances can be wear of the tool or play in the bearings of the lathe. In order to check the process result, the diameter must of course be measured, for example with a caliper or an outside micrometer. The measuring instrument itself must be suitable for the task. In order to prove this, we can use different methods. For example, the MSA. This stands for Measurement System Analysis. This is the subject of a separate lesson. When measured values are written down in the order in which they occur, such a list is called a master list or a raw data table. A disadvantage of such a list is that you cannot read the desired information directly from it, such as extreme values or mean values. The data must therefore be further processed. With the help of a software, the first important characteristic values, such as maximum value, minimum value, or the arithmetic mean, can then easily be determined. Visualizing the data in a histogram is another important way to assess the process result. Here you can see very nicely how the values are distributed around the target dimension. What you do not want to see is, for example, that the values accumulate at one of the tolerance limits. This would increase the likelihood that some parts will sometimes not meet the specifications. An important intermediate step for further calculations is to describe the value distribution using a curve that can be described mathematically. A classic example of such an envelope curve would be the Gaussian distribution. Once you have managed to describe the distribution of the values mathematically, you can also calculate the probability that a process will produce characteristics that are outside of the specification. The process location, the variance of the values, and the specification of the characteristic are important values for this. But instead of directly specifying a probability in percent, so-called machine or process capabilities are specified. How to calculate and interpret these is the subject of the following lessons of this training. Well, that was a lot of new information. Therefore, I would like to conclude by repeating the 3 most important key messages. The consistent application of the methods of statistical process control helps to produce high-quality products that hopefully satisfy the customers. The variance and the process location of processes are important influencing factors on product quality. And last but not least, SPC helps to keep scrap small. If you found this lesson helpful, please let me know and leave a comment. Thank you for that. Take care and see you next time. Bye.